So I want to tell you about the junction tree in general, or about cluster graphs. Junction trees are a specific incarnation of cluster graphs with an additional property, the so-called running intersection property holding. Now, if you look at this summation here, I could arrange these factors in an optimal way. So, for instance, so don't laugh at me when I'm drawing this now. These are parentheses, in case you didn't guess. Okay, so these parentheses are a summary of how you could arrange the terms over there. So how exactly? So we have step number 1, which would be at the which we do first. So this is at the very inside. So this is the closing parentheses of step number 1. Step number 2 is actually, we've done it just after step 1, but it's actually unrelated. You see, because this involves a B, E, and I, and this involves A, B, and F, and B is only summed out much, much later. So at this stage, they're nothing to do with each other, and step number 2 is actually here. So where is this factor first used? It is first used in step number 4. So this is the closing parentheses of step 4, and the result of 4 is used in step number 5. So I'm looking, you see what's generated in 4, and where is this used? It's used in 5. Then we had the result of 3, and so the results of 3 and 5 together are used in step 7. The results of 3 and the results of 5 are used together in step 7. This is what this parenthesis here is saying. And we can go on like that, and we'll find so this is an optimum nesting of the terms, because you see, if a naive nesting of the same terms would be to have all parentheses opening and then all parentheses closing, which is in a way the way that the results are presented here. But by grouping the terms here, I will need less summations overall. So while this is mathematically equivalent and this is a smart way, this is pretty hard to read. I'm sure you will agree. So we can find a nicer way of writing that same content. And if you might have seen in algorithms and data structures that if you want to parse a mathematical expression, you can also arrange that in a tree. And this is something we can also do here. So at the very first stage, we were involving the variables A, B, and F. And so where did we use that? The new factor, we sent out a message tau of B and F, and this was used in step number 4. And in step number 4, we involve the variables b, f, g, and j. So I'm now drawing a cluster graph where each cluster holds all the variables that need to be evaluated together at any one time. So essentially, I'm arranging these terms here into a graph. Now the result of step number 4 was tau of b, g, and j, which in its turn was used in step number 5. And 5 involved the variables b, c, g, and j. And in step number 5, we created a new factor, which was used in step number 7. And this is where things get interesting for the first time. Remember that you see 7 was this parenthesis here. So we have one, should we say, leaf of our tree here, there, and there. So 7 also accepted input or a message from step number 3. And step number 3 had involved the variables c, d, and h, and sent a message regarding c and h, or a function of c and h. So you will we can see we can make a couple of observations here. We're not done yet, but observations which can actually be proven. There is the running intersection property. The running intersection property states that if a variable is found in 2 nodes of this cluster graph, of this junction tree, it also needs to be found on all the nodes that lie on a path between these points. Because it is a tree, we only have anyway a single path between any 2 nodes. So, for example, let's take J appears here and there, so it must also appear at all intermediate positions. So if a variable x is in cluster I and cluster J, then it must also be found at all intervening clusters along the unique path that connects Ci and Cj. And secondly, if you look at the structure of these messages always comprise or have in their scope those variables that appear in both nodes. So you see here what do these nodes have in common? Only b and f. So the message is a function of b and f. What do these nodes have in common? B, G, and J. So the message is a function of B, G, and J. What do these nodes have in common? B, C, no, C not. Must be some error here. B, C, B, C, J, and H. So these two nodes have in common B, C, and J. So the message that we send is a function of B, C, and J. And this holds true in general. So the messages that are sent between two clusters have a scope of the intersection of the one cluster and the other cluster. So a message is sent here, I should say, between from CI to CJ, have a scope that is the intersection of the two clusters. Okay, so that was step number 7. Then in step number 8, we had a function of, or the variables involved were B, J, H, and K. And the message sent from 7 to 8 was tau of BHJ. But 8, look, this is this parenthesis here. It also received input elsewhere. So that also received input from step number 6. Tau of BH and K. And 6 itself involved BHI and K. And 6 in turn involved tau of BI, which was computed in step 2. No, 2 involved, sorry, BE and I. Okay, and then 8, where was the result of 8 used? That was used in step number 9. We're almost there. So this sent a message tau of J and L to the final cluster, which involved only J and L in step number 11. Okay, so you see that we have a tree with a single root, and we have been pushing messages along this cluster graph to compute the marginal of interest, to compute the marginal of L. compute the marginal of one variable which was of interest to us, so of some query variable. So please note that this set of nested equations here is really the same thing as the way that we've sent messages along that graph here. Now, for a given sequence of variable eliminations, we get a given junction tree. And a bad sequence will result in a bad junction tree, which will have factors depending on many variables somewhere in the middle. But now, given this junction tree, we could pass messages in other directions. So let's say that if we are, so, I will add undirected edges to make clear the distinction between really the structure of the graph, which cannot be modified, and the direction in which messages were sent, which can be modified. So let's say these messages which were sent in this particular direction here, these messages correspond to this ordering of parentheses shown here. Yeah, sorry, and this the set of parentheses that's really structurally equivalent to this entire junction tree. I'm trying to figure out if the direction of messages can lead to a different set of parentheses or not. Yes, it can. So this is why it's correct that I put an orange box around this here. So this is just a graphical summary so far of what we have done anyways. So if we just want to perform a single query, if we're just interested in the probability of horse number L being healthy or pure or a carrier, this is what we could do. But if we now want to make another query, so let's say we are interested in K, for example, horse number K, then naively we could just start with variable elimination all over again to make a statement about k, or we could send messages in a different fashion and concentrate on a specific node involving k, and then compute these probabilities of k from that node. So let me give you a concrete example. So let's say that we're interested in node number 3. I could now send messages the following way. And the root of my tree would then be this one here. And I would get out with this factor depending on C, D, and H. And from this factor here, I could then solve for the actual probabilities that I'm interested in. Now the important point is the following, that these messages which I'm sending out here, these are identical, because at this stage the algorithm does not know if the root is going to be this way or that. So these messages are identical. These messages are also identical. So I can reuse the same messages to compute different queries. And now the most general answer possible is if you compute, but you see here the messages went in the other direction. So orange went in this direction, green went in that direction. So if you now compute the messages in both directions everywhere on each edge in this cluster graph, you are then well equipped to answer queries regarding any node. So if you have a graphical model with many nodes and you want to make a prediction of the probabilities in one node, you don't need to do that from scratch for every target node or for every query node, but you need to build this junction tree just once. You need to find the messages in both directions for each edge just once, and then by propagating these messages you can compute any of the queries of interest. So this is the strength or the appeal of this algorithm. So let me add as an observation, a message from cluster I to cluster J does not depend on which node is picked as root, assuming here that the root lies somewhere beyond cluster number J. So as a consequence, you can reuse messages to compute all different kinds of queries. And this recycling of results, that is at the heart of dynamic programming. So the dynamic programming applies whenever you have many similar problems to solve, and whenever a partial solution to one problem is also a partial solution to the other problem. And that is the case here. Okay. So in summary, what the junction tree allows is to store all these partial results for reuse later on. And a junction tree is called calibrated if messages have been sent along both directions. So a junction tree is calibrated once messages have been sent from all leaves to some random root, and then from the root back to all leaves. And note also that the root does not need to lie. So in these two examples here, I picked the root at these extremes of this tree structure, of this graph. But the root can really be anywhere. So I could also make this point, or I could make this cluster here the root. So the important point is that I send messages from everywhere to the root, and then back from the root to all other nodes. And once a tree has been calibrated, on a calibrated tree, the posterior distribution of any set of variables that are together in one cluster can be computed. And the messages for this algorithm to work, the messages must be sent in strict order. Meaning that we only send a message from a cluster once the cluster has received all necessary input. Before it sends itself. And taken together, we can write down the sum product algorithm for message passing in junction trees. Where messages look as follows. So message delta ij from a cluster I to a cluster j is then given by we have the sum and the product. So we sum over all variables from Ci that are not shared with Cj. So these are the variables that are common to both factors, and we sum out all variables that are not common to both factors here. And then we have a product of what I called the native potential times all the incoming messages. So we have a product over all the neighbors of node I except node number j. And then a product over all the incoming messages into node I. So this is the neighbors. And psi I, this native potential of a cluster, is the product over all factors where the factors are chosen to belong to that particular node. So the factors are chosen such that alpha of phi is I, and alpha of phi, this is the clique that factor phi belongs to. So in other words, these psi's, these are these terms that summarize the terms that had here been written as phi's, and the product of the incoming messages corresponds to these tau's here, or to the products of these tau's. Okay, and I called it native potential. I think the official name is initial potential of cluster I. Okay, and in directed graphical models, this corresponds to variable elimination, and hence this algorithm is exact in Bayesian networks. So, what have we done? I think everybody agreed with this first formula here, where we had simply exploited the fact that L depends, for instance, only on its parents and not on variables further up. So this equality here, it's on the one hand means marginalizing out, and on the other hand, we've simply used this factorizing of joint probability distributions in Bayesian networks. Then we have seen that not every factor here depends on all variables, and we can hence pull some of these integration signs in. And if we do so, and if we integrate our terms, we generate new factors that are functions of all variables except those summed out, which are then used in some other summons. So this formula could be rewritten, for instance, like that for a given particular ordering of the variables. I could have used any other ordering, so I could have summed out first A and then B and then C and so on, but I would have obtained a less compact factors and less compact messages. Now, this junction tree here is the structure of this junction tree is determined by this order of variable eliminations, and there's a one-to-one correspondence. So this variable elimination gives that junction tree. However, the junction tree, what it determines out of the junction tree is only the structure, so where we have these undirected edges between the clusters. We still have the liberty of deciding in which way we want to send messages. So do we want to send messages in this direction? And again, all messages are functions only of those variables that appear in both clusters. Or do we want to send messages in that direction? If we send messages from everywhere to a particular node, for example, this one up there, we need to do so in the strictly correct order, meaning this guy can only send its messages when it has had, when it has received its incoming messages. So as a matter of fact, we need to start here at these leaves and can then propagate these messages up to our root node. We then have the marginal posterior probability of all these factors that appear together in that root node. But we can pick any node as root node. In particular, by rather than picking several root nodes, what we can do is we can propagate to one root node and then send messages back from this root node to the entire rest of the graph. And we then have messages pointing in both directions for every edge. And this allows us to compute the posterior probability of any sets of variables that appear together in one clique. So let's say if I'm interested in more color. We have not used pink. So if I'm interested in this one here, I could use, and once I have computed these bidirectional messages along edges, I can simply propagate all these messages up to this node here, and I then obtain the posterior probability of all these variables here together. So I obtain, and not all of these clusters, you know, for instance, the one that I've circled here, there is no simple probability that this one corresponds to. But others, but I can still solve for individual variables if I like. But others I can directly read off from the graph. So for example, if I take that as my root node, if I propagate all messages here, what I then get is the posterior probability of this product here. Okay, so not so many of you have stud farms. So why do you care? So first of all, I've taken this rather big numerical example because you know, the textbook example is typically given is about you know, the grass being wet and you don't know if it was the rain or the sprinkler, which is much more compact. However, what I liked about this example is that you know, at least the probabilities in this graph and so on are meaningful, in the sense that we can use these Mendelian genetics to really derive what the conditional probability tables are. But as I said, you know, stud farms are not so relevant to many of you. However, if you go back to the first note of today's lectures, I said that directed graphical models, they encompass some of the most fundamental algorithms that we have. And in particular, I mentioned hidden Markov models and Kalman filters, which are for discrete and continuous hidden states, respectively. And the beauty is that, so given fundamental algorithms like this message passing here, can now be applied to all of these algorithms that can be expressed as graphical models. So for example, hidden Markov model has an algorithm which is known as the forward-backward algorithm. And this algorithm used to be standalone. So it was clear that it had something to do with dynamic programming, but the connection to the rest of pattern recognition was not quite clear. And now we have, or today one has the insight that this is actually just a specific embodiment of this sum product message passing applied to this very particular graph structure that hidden Markov models have. And so one good reason to learn about all this is that some of the most fundamental existing algorithms can be understood and summarized in these terms. Another good reason is that some of the most recent algorithms, they have been put forward in the shape of graphical models. So you could probably still use them without, in principle, but it wouldn't make sense because even the people who have developed them, when they wrote down the structure of the algorithm, they've been thinking in terms of graphical models. And I've mentioned PLSA as one example, so partial latent semantic analysis, but there are much more complicated graphical models that people use today, both directed and undirected. So in the exercise, you'll be able to play a little with this for yourself. And the next time, we will look at directed graphical models that are of more broad relevance to pattern recognition than the very specific example we've looked at today. Have a nice week.